What if I tell you that light is one of the most fascinating and mysterious things in the universe? Light is a form of energy that travels at an incredible speed of 300,000 kilometers per second. Light can behave as a wave or as a particle, depending on how we observe it. Light can have different colors, which depend on its wavelength. Light can reflect, refract, diffract and polarize. Light can create beautiful natural phenomena such as the rainbow, the solar halo and the aurora borealis. Light can be used to communicate, to explore space, to generate electricity and to cure diseases. Light is, in short, a wonder of nature that deserves to be studied and admired. In this video, we invite you to discover more about light and its properties. Get ready to illuminate your mind with this fascinating topic. Light is a form of electromagnetic radiation that can be detected by the human eye. It has properties in common with both waves and particles, depending on how we observe it. Light can travel through empty space at a constant speed of about 300,000 kilometers per second, which is one of the fundamental constants of nature. Light can also interact with matter in various ways, such as reflection, refraction, absorption, emission, scattering, and polarization. Light has different characteristics depending on its frequency, wavelength, and energy. Frequency is the number of cycles of a wave that pass a point per second. Wavelength is the distance between two successive peaks or troughs of a wave. Energy is the amount of work that can be done by a wave or a particle. The relationship between these three quantities is given by the equation $E equals H nu equals frec Hc lambda $W $E is the energy, $H is the Planck constant, $nu is the frequency, $C is the speed of light, and lambda is the wavelength. The electromagnetic spectrum is the range of all possible frequencies of electromagnetic radiation. It includes radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays. Each type of radiation has different applications and effects on matter. Visible light is the part of the electromagnetic spectrum that humans can see. It ranges from red to violet, with wavelengths from about 700 nanometers, nm, to about 400 nm. The different colors of visible light correspond to different wavelengths and frequencies. For example, red light has a longer wavelength and a lower frequency than violet light. The colors of visible light can be combined to form white light or split into a spectrum by a prism or a rainbow. Light is essential for life on Earth, as it provides energy for photosynthesis, drives global weather patterns, and allows us to perceive the world and communicate within it. Light also helps us explore the universe, as it carries information from distant stars and galaxies. Light is a fascinating and mysterious phenomenon that has intrigued scientists and artists for centuries. Light is a form of electromagnetic radiation that can interact with matter in various ways, depending on the frequency, wavelength, and energy of the light and the properties of the matter. Some of the possible interactions are: reflection. Light bounces off the surface of an object. The angle of incidence is equal to the angle of reflection. Reflection can be specular, mirror-like, or diffuse, scattered, depending on the smoothness of the surface. Refraction. Light changes direction when it passes from one medium to another with a different refractive index. The refractive index is a measure of how much the speed of light is reduced in a medium. Refraction can cause phenomena such as dispersion, splitting of white light into a spectrum by a prism, and total internal reflection, when light is trapped inside a medium by exceeding the critical angle. Absorption. Light transfers its energy to the atoms or molecules of an object, causing them to vibrate or rotate. The amount of absorption depends on the frequency of the light and the energy levels of the matter. Some materials can absorb specific frequencies of light and emit them later, which is called fluorescence or phosphorescence. Emission. Light is produced by the atoms or molecules of an object when they return to a lower energy state after being excited by heat, electricity, or other forms of energy. The frequency of the emitted light depends on the energy difference between the initial and final states. Emission can be spontaneous, random, or stimulated, coherent, as in lasers. Scattering. Light is deflected by small particles in a medium, such as dust, air molecules, or water droplets. The amount and direction of scattering depend on the size, shape, and composition of the particles and the wavelength of the light. Scattering can cause phenomena such as blue sky, red sunset, and rainbow. Polarization. Light is composed of electric and magnetic fields that oscillate in planes perpendicular to the direction of propagation. Polarization is the orientation of these planes. Light can be polarized by reflection, refraction, scattering, or by passing through a polarizing filter. Polarization can be used to reduce glare, enhance contrast, or analyze the structure of matter. These are some of the ways that light interacts with matter, but there are more complex and subtle effects that require more advanced physics to explain. Scattering is the process in which a wave or a particle changes its direction or energy due to the interaction with another wave, particle, or an obstacle. Scattering can occur in different ways, depending on the type and size of the scatterer, the wavelength and frequency of the incident wave or particle, and the angle of incidence and observation. One way to classify scattering is by the size of the scatterer relative to the wavelength of the incident wave. For example, if the scatterer is much smaller than the wavelength, such as a molecule or dust particle, the scattering is called Rayleigh scattering. This type of scattering is responsible for the blue color of the sky and the red color of the sunset, as it scatters shorter wavelengths, blue, more than longer wavelengths, red. Rayleigh scattering is inversely proportional to the fourth power of the wavelength, which means that blue light is scattered about 16 times more than red light by the same particle. Another way to classify scattering is by the shape and structure of the scatterer. For example, if the scatterer is spherical and has a uniform refractive index, such as a water droplet or a bubble, the scattering is called Rayleigh scattering. This type of scattering is responsible for the white color of clouds and fog, as it scatters all wavelengths equally. Rayleigh scattering depends on the ratio of the diameter of the sphere to the wavelength of the incident wave, and it can produce different patterns of intensity depending on this ratio. A third way to classify scattering is by the nature of the interaction between the incident wave or particle and the scatterer. For example, if the interaction involves a change in energy or frequency of the incident wave or particle, such as when an electron absorbs and emits a photon, or when a nucleus deflects an alpha particle, the scattering is called inelastic scattering. This type of scattering can reveal information about the internal structure and energy levels of the scatterer. Inelastic scattering can be further divided into subtypes such as Compton scattering, Raman scattering, and Rutherford scattering, depending on the specific mechanism involved. These are some of the ways to understand scattering and its types. Compton scattering is the phenomenon in which a photon collides with a charged particle, usually an electron, and loses some of its energy and momentum. The photon is scattered at an angle from its original direction, and its wavelength is increased. The amount of wavelength shift depends on the angle of scattering and the energy of the photon. One example of Compton scattering is the Snellius-Zeldovich effect, which occurs when cosmic microwave background (CMB) photons are scattered by hot electrons in galaxy clusters. The CMB photons have a very low energy and a very long wavelength, but when they encounter the electrons in the cluster, they gain some energy and momentum from them. The CMB photons are then scattered at different angles, and their wavelength is decreased. This causes a distortion in the observed CMB spectrum, which can be used to measure the properties of the galaxy cluster and the CMB itself. One another example of Compton scattering is inverse Compton scattering, which occurs when a low-energy photon is scattered by a high-energy charged particle, such as an electron. In this case, the photon gains energy and momentum from the particle, and its wavelength is decreased. The photon is scattered at an angle from its original direction, and its frequency is increased. Inverse Compton scattering can produce very high-energy photons, such as X-rays or gamma rays. One application of inverse Compton scattering is in astrophysics, where it can explain the emission of gamma rays from pulsars and active galactic nuclei. These sources have very energetic electrons that can scatter ambient photons, such as starlight or CMB photons, and boost them to gamma ray energies. Inverse Compton scattering can also occur in particle accelerators, where electrons are accelerated to very high speeds and collide with photons from lasers or synchrotron radiation. 3. The Compton effect is a phenomenon that occurs when a photon, a quantum of light, collides with an electron and transfers some of its energy and momentum to it. As a result, the photon is scattered with a lower energy and a longer wavelength than before the collision. The change in wavelength depends on the angle of scattering and the mass of the electron. The Compton effect was discovered by Arthur Compton in 1923, and it provided strong evidence for the particle nature of light. 12. To understand the Compton effect, we need to consider the properties of photons and electrons. A photon is a massless particle that carries energy and momentum proportional to its frequency and inversely proportional to its wavelength. An electron is a massive particle that has a rest mass and a kinetic energy depending on its speed. When a photon collides with an electron, it behaves like a billiard ball and transfers some of its energy and momentum to the electron, which recoils with a higher speed. The photon also changes its direction and frequency after the collision. The conservation of energy and momentum in this process leads to the following formula for the change in wavelength of the photon. Equals mech 1 cos, where under the initial and final wavelengths of the photon, h is Planck's constant, m is the rest mass of the electron, c is the speed of light, and is the angle between the initial and final directions of the photon. This formula is known as the Compton formula or the Compton shift. It shows that the change in wavelength is independent of the initial wavelength of the photon, but it depends on the angle of scattering and the mass of the electron. The term mech is called the Compton wavelength of the electron, and it has a value of about 2.41012 meters. The Compton effect can be observed when high-energy photons, such as X-rays or gamma rays, are scattered by loosely bound electrons in matter, such as graphite or metals. The scattered photons have a lower energy and a longer wavelength than the incident photons, and this difference can be measured by using detectors or spectrometers. The Compton effect demonstrates that light has both wave and particle properties, and it supports the quantum theory of radiation. It also has important applications in fields such as nuclear physics, astrophysics, and medical imaging. Light is a fascinating phenomenon that has been studied by many scientists and philosophers throughout history. Here are some of the main points from the web search results. Light or visible light is electromagnetic radiation that can be perceived by the human eye. It has a wavelength range of 400 to 700 nanometers, (nm), and a frequency range of 750,420 terahertz. Light can also refer to electromagnetic radiation of any wavelength, whether visible or not. The study of light, known as optics, is an important research area in modern physics. Light can be analyzed as both waves and particles, and it propagates by massless elementary particles called photons. The speed of light in vacuum, 299,792,458 meters per second, is one of the fundamental constants of nature. The main source of natural light on Earth is the sun. Historically, another important source of light for humans has been fire, from ancient campfires to modern kerosene lamps. With the development of electric lights and power systems, electric lighting has effectively replaced firelight. The search for the true nature of light goes back centuries and includes contributions from some of the most illustrious scientists in history. Some of the historical theories about light are: in the 5th century BC, Empedocles postulated that everything was composed of 4 elements: earth, air, fire, and water. He also suggested that light was emitted from the eyes and interacted with the environment to enable vision. In the 4th century BC, Plato and Aristotle argued that light was a stream of tiny particles emitted by a source or reflected by an object. They also believed that vision was possible because these particles entered the eyes. In the 3rd century BC, Euclid wrote a treatise on optics, in which he described the laws of reflection and refraction. He also proposed that light travels in straight lines and that the angle of incidence equals the angle of reflection. In the 2nd century AD, Ptolemy expanded on Euclid's work and measured the angles of refraction for different media. He also introduced the concept of color as a property of light. In the 10th century AD, Ibn al-Haytham, also known as Al-Lazan, wrote a book on optics, in which he rejected the emission theory of vision and proposed that light was reflected from objects into the eyes. He also explained how lenses work and how the eye functions as an optical instrument. He also performed experiments on reflection, refraction, dispersion, diffraction, and interference of light. In the 17th century AD, Isaac Newton demonstrated that white light was composed of different colors by using a prism to split it into a spectrum. He also proposed that light was made up of corpuscles or particles that obey the laws of mechanics. He explained reflection and refraction by assuming that light particles were attracted or repelled by different media. In the 18th century AD, Thomas Young and Augustin Jean Fresnel showed that light was a wave phenomenon by performing experiments on interference and diffraction. They also explained polarization and color phenomena by introducing the concept of transverse waves with different orientations. In the 19th century AD, James Clerk Maxwell unified electricity and magnetism into a single theory of electromagnetism. He also derived equations that described how electromagnetic waves propagate in space and time. He predicted that light was an electromagnetic wave with a specific wavelength and frequency range. In the 20th century AD, Albert Einstein explained the photoelectric effect by proposing that light was composed of discrete packets or quanta of energy called photons. He also showed that light had both wave and particle properties, depending on how it was observed. This led to the development of quantum mechanics and quantum optics, which describe the behavior of light at the atomic and subatomic level. That's all. Bye.